So now we're going to start talking about different types of factors that influence the way that reactions happen or their mechanisms, okay? So we need to start with the basics, and that is comparing electrophiles and nucleophiles. Now, you all might realize already that electrophiles and nucleophiles is another way of saying things that are attracted to negatively charged things and positively charged things. Because remember, the term phile means lover of that thing. And what's in a nucleus is stuff that's positively charged. So a nucleophile is something that is attracted to positive charges. What that means is that it's probably negatively charged, or it has extra electrons that can go and react somewhere. So I often denote this as a nucleophile with two lone pair of electrons if we're just shorthanding things. And those electrons are then going to go towards something that is partially positively charged. Now don't get this confused with the other arrows that I use later in this lesson, but see how we've got here like a pair of extra electrons that's making a double bond. Well, that extra electrons, those would be nucleophilic. Or you can consider these electrons on the oxygen, either pair, it's the same thing, would be nucleophilic because there is a partial negative charge on that oxygen, which means that it will be attracted towards nuclei or something that's partially positive or actually positively charged. Okay. On the other hand, we have electrophiles. So electrophiles are things that are attracted to these negative charges. These are Lewis acids, basically. So things that are electrophiles include partially positive atoms or carbocations. There's lots of things that this will include, okay? So when we're talking about reactions and mechanisms, what we're trying to also think about is that when we're showing reactions, nucleophiles are what attack electrophiles. Electrons are what is going to move. You don't go up and high five somebody with their kidney, okay? You touch people with the outside of your body, which is like your skin. Well, that's how electrons work too. That's how reactions work, is that electrons go and move around. Positive charges will move as a reaction to where electrons are going. So realize that. Electrons are what's moving. So let's say that we have a nucleophile that we have these two electrons on, and we're showing in there where this arrow goes to the electrophile. What that's really showing is that there's now a new bond that's being formed. So if a nucleophile comes out and grabs an electrophile, then that's showing that you've got a new bond that's there. Okay, so there's this other term. It's really very much like what it sounds like. It's called a leaving group. Leaving groups are called leaving groups because they leave. And so what can happen is that we can have a leaving group go and break that bond. And that will basically make this electron pair right there be right there. And what that does is it leaves behind a positive charge. Why? Because that leaving group took the electrons from that bond with it. So you only have 3 bonds on that carbon, and therefore it has a formal charge of +1. So that's the way those look. Okay, proton transfers are still going to be led by electron movement. So the electrons in, say, this oxygen right here will come and grab a hydrogen. And in this case, the bond that is between that oxygen and that hydrogen must therefore break as a response. Why? Because hydrogen can only handle 2 electrons at a time. It cannot handle having 2 bonds. And so that means that the electrons will then go back to that oxygen. That gives you a new bond between that oxygen and hydrogen. That will leave a formal charge of a +1 on that oxygen. Notice that we have a formal charge on the left that is the same as the one on the right, just like we did before, okay? You can also have proton transfers that occur with, let's say, a base. And so in this case, we can have electrons come and grab that hydrogen. And I don't know if you can see it, but there's a little arrow that's also pointing the bond with that hydrogen is moving back towards the carbon that's there. This would be a resonance stabilized negative charge here. And again, the charge on the left-hand side of this reaction and that on the right is the same. Okay. Next, we have methyl anhydride shifts. So this is something that you do need to really understand. So the first thing I want us to look at is this chart that we see here. What I see is that we've got CH3 with a positive charge, then what I would label as a primary, secondary, and tertiary carbocation. Well, this series sort of makes sense. We can stabilize the positive charge by having more R groups that are surrounding that carbon. That's kind of like having more friends to help support your positive charge, whatever it is, on that carbon. So let's say that you have an accident happen and you need more friends around to help take care of whatever that accident is. The more the merrier, right? The more people that are willing to help you, the better off you are. That's kind of what's happening here. You can only get to so much of a good place though until somebody's actually willing to take over the burden for you. And so that would be sort of what we see in both of these cases. So resonance helps stabilizes that positive charge. Keep in mind, if we move those electrons there, we could actually end up having a positive charge move over. So positive charge moves as a reaction to the electrons moving. So keep that in mind. That's what's happening. In the benzylic position, there's multiple resonance structures that can happen here, and that's why that's the most stable of all of them. So in order to make more stable positive charges or carbocations, we can shift either a methyl group or a hydrogen. Now a hydrogen is going to shift more easily because it's smaller. That's the simple reason why. But a methyl group can also shift in order to help stabilize a positive charge. Again, you're showing where electrons move, a positive charge is left as a result. I kind of see a positive charge as like a hole because that's kind of like where there's not a bond to carbon that should be there. So in other words, you only have 3 bonds to carbon instead of 4. Okay, so a methyl shift would simply be taking a methyl group and moving it over towards that carbocation. And so what is going to result there is you're going to get a positive charge there because you took a bond from this carbon right here and you moved it over. So you take it and leave a hole in this spot right there, and that's where you get the carbocation there. And the same thing could happen if you have a hydrogen that shifts over, is that we leave behind a positive charge there. That can also happen for allylic stabilization or benzylic stabilization. So we could have a hydrogen shift over to a carbon there, and that would leave behind the hole that's right there. Okay, good. Okay. When it comes to doing mechanisms, there's a lot of things we have to consider. I see this sort of as windshield washers, or windshield wipers, sorry. When one of them moves, both of them move. So a lot of times there's one arrow that leads to another arrow, or sometimes more than just 2. So let's say that SH is looking for a place to live. Those electrons on SH might identify that this carbon right here is partially positive, and this bromine right here is partially negative. So these electrons are naturally going to be attracted to that carbon right there. When that goes and gets attacked, so when the SH goes and attacks that carbon, well, that carbon doesn't have a positive charge. It's not going to hold there. In other words, you've got 8 electrons on that carbon. It can't have 10. So as a result, this bromine has to get kicked out. So when that bromine leaves, it gets 2 extra electrons that are there. And then a new bond is forming right here between that sulfur and the carbon. This is something that you have to practice. This is not something that you're going to naturally just know. This is something that you seriously have to practice, and we're going to keep working on it for quite some time. But this is the foundation for the rest of Organic 1 and all of Organic 2. So it is really important. So good luck. Make sure you practice.